right, everybody. Yep. So this is serendipity. She's in heat right now, but we can't get her operated on because she's got heart difficulties. But she's going to make a lot of noise. So I thought, you would enjoy seeing her first. So she's being very annoying. We can remember who she is and not get too upset. Okay. She also doesn't like to be held. So that was about as much tolerance as she's going to have for me. Okay, so let's go ahead and share the screen and let's go with that. Okay. All right. So today we are going to talk about surface areas, and my apologies. This is going to feel very reminiscent of chapter 6. See, just got a lot to say about this, and I apologize that it's going to feel like it's a little bit hard. Okay, at least for the first part. Okay, so not quite as bad though. So what we're going to talk about today, we have surface area. We don't have like a special symbol for surface area. We just have area. Okay, but what we're going to do is we have a cone here, right? And we have an R here, right? And we have an L. All right. Now what we're going to do is we're going to make a little cut, okay, in our cone, and we're going to flatten it out. Okay, so if I flatten my cone out, right, we should get something that kind of looks like that, right? And then what are we looking at here? We're looking at L, right? And do you remember that when we first introduced you to radians, of course you do, like it was yesterday, we used the formula for arc length, not the arc length yesterday, but the arc length for circles, which was S was equal to R theta, as far as theta was in the was in radians. Okay, so this here, right, this circumference down here, what is this? It's 2 pi r, right? So the theta. So what I'm going to say is that this part of my circle here, right, the arc length is, right, this is this is r theta, and this is L times theta. Okay, but what's my arc length? My arc length is 2 pi r. My radius in this case is L, right? Because in this circle, my radius is now L. I promise you that when we do this, this is going to be a little confusing to set it up, but it's worth going through this confusion because what we're going to do next is we're going to work with some more cones, and it'll look right with the cones in the next section, even though this is kind of confusing. Like usually we call this R, even though it's L now, and we usually call this something else, like with an L, and now it's R. Okay, so this is going to be, this is just going to be 2 pi r rather. Okay, so that's 2 pi r's. Okay, and here we have for L. Okay. So the area here, right? Well, actually not quite yet the area. Right? Do you remember that the area of a circle is pi r squared? What I'd like to do is figure out, like, well, how do we get the part of a circle, right? The section of a circle. And again, if you remember going back to trig, right? I'd really like a theta in here. So how many angles like is all the way around a circle? And that's 2 pi squared. I needed a 1/2 here in order to make this actually fit. Okay, so the formula for the sector of a circle, the area of a sector, that was 1/2 theta r squared. Okay, I'm sure if you go back and look at your chapter 1 in trigonometry, or like, you know, if you kept them, your first page of notes from your trigonometry class, I'm sure you all have. I never did, so whatever. All right, but there we have that. Okay, and the next thing we're going to do is like, well, this theta, right? This theta is equal to, right, 2 pi over L. So we can get the area of the sector, 1/2 theta is 2 pi r over L. And in our case, right, this is an r squared. This is going to be L. For our specific case, right, the radius is L squared. Right, that's what that job is doing there. So we're going to go ahead and cancel. Right, we're going to go ahead and cancel, and we get the area of the cone that I have here, the surface area of the cone, is equal to pi r L. Okay, going back to what the cone is labeled here. Okay, so the surface area here is pi r. All right. All right, so that's the first part of all of that. Okay, so we have surface area of cone is pi r L. Okay, next thing we have to set up, okay, is we are going to figure out the area, the surface area of a frustum. Okay, so what we're going to do here is we're going to draw another cone. I'm going to cut it in half. Okay, put a little marker down the middle here, and we're going to have an R1 here. We're going to have an R2 here. Okay, I'm going to make this an L2. I'm going to make this an L1. Okay, so frustum is just like this part of the cone. Okay, that's the frustum. So when you buy coffee, right, they don't give you a cup that's that small though. Okay, but when you buy coffee at a convenience store, you buy coffee at Starbucks, right? Technically, you're buying a cup, but you're buying a frustum of coffee. Okay, so you can remember that. And what we're going to do here, okay, so our plan is that we're going to get our, a random curve here. We're going to rotate it. Okay, so you got the same thing down here. I can't draw that. But the idea here is that we're going to come up and we're going to have all of these tiny little, see, that kind of makes a frustum, right? And we're going to add up all of these pieces, okay? So we have to figure out the surface area of this thing in order to apply it to the surface area of this, all these tiny little ribbons here. Okay, so this is what we're getting this ribbon. Okay, and we're just going to add all of these up. That's where the calculus is going to come in, is we're going to add up all these tiny little pieces here. Okay, so that's what we have. Okay, so recall, right, my area was equal to pi r L. Right, so the radius times pi r radius times L. That's all right. That's my surface area here. So what we're going to do here is we're going to take the big cone and we're going to subtract the little cone from it. One thing we have to do before we have to go into that is I have to make a little relationship here so that we can say something about the fact that this triangle, right? So you think about, right? Think about this, is that the this theta here, right, is the adjacent over the hypotenuse. So this is a cosine, right, of that angle. The cosine of this angle would be, oh no, it wouldn't. Cosine of this angle here would be the R1 over L1. That would be the sine. Okay, and that would be divided by, let's find another color here that's bold. Okay. Okay. That the sine of these two angles are the same. So by similar triangles, we're going to say something clever like the sine of this angle is equal to the sine of that angle. Okay, because L1 plus L2 would be the whole hypotenuse. R2 would be the opposite side in this case. And then for the little triangle, we'd have R1 over L1. So all we're doing is saying that the sine of this angle is equal to the sine of this angle. Okay, so sine of theta equals sine theta. That's similar triangles. Okay, So we have that relationship going. All right. So next up. So what we're going to do is we're going to take the big area, right? The big area minus the little area. And that should be the frustum area. Okay, so big area minus little area. That's all we're doing. So the big area, let's go down here. We'll say the big cone. Right, that was pi r2 L1 plus L2 minus, and this is the little cone. It's pi R1 L1. Right? And then we're going to do a little bit of changing things around. Okay, that's my surface area of my coffee cup, or my coffee cup for Starbucks there. Okay, so let's go ahead and do some stuff. Let's do some magic here. So we've got, I'm going to pull the pi's out of everything, I think. Yeah, let's just pull the pi's out of everything. So I'm going to have R2L1 plus R2L2 minus R1L1. All right. And then I'm just going to recombine these. So R2L1 minus R1L1 minus R2L2. Right? And now we're just going to factor this out. So we're going to say this is R2 minus R1, L1. Oops, that's not a minus anymore, right? This is a plus R2, L2. Plus. So all I did was group the stuff with the L1s together, and then we left the stuff with the L2s somewhere else. Okay. Why would we have done that? Well, let's go back to this. Okay. So remember that L1 over R1. Oops, R1 over L1. Okay, either way. Let's go ahead and write it down the way I have it. So we're going to say, right, what do we have here? We have R1 over L1 is equal to R2 over L1 plus L2. I need it in the other direction now. So we're going to go ahead and say that L1 over R1 is equal to L1 plus L2 over R2. Okay, reciprocal rule, that's fine. We just invert both sides, right? If A is equal to 3, then 1 over A is equal to 1 over 3. All right, and now we're just going to perform a little algebraic magic here. We're going to say, well, this is R2L1 is equal to, right, cross multiplying. So this is just going to be R1L1 plus R1L2. All right. So what else can we say about this? We could say that we can pull this over the other side. So we have R2L1 minus R1L1, R1L2. Okay. So here, right? Square here or something. Okay. R2, and this is also going to be, right, R2 minus R1, L1 is equal to R2, or R1 rather, L2. Okay. Let's go ahead and make it happen. Okay. I mean, naturally, I would assume you just would have arrived at all the conclusions and all this on your own, right? It's just, that's how that happens. We're just all that brilliant. Okay. So going back to my original here, we're going back to my area. Okay. So from 1, we're going to remember that area was equal to pi. And what did I have here? I had R2 minus R1, L1 plus R2, excuse me, L2. Okay. And we can substitute something here, can't we? We have R2 minus R1, R2 minus R1, L1. That's equal to R1 L2 plus R2 L2. All right. Now we're going to say that this is L2. Okay, we still have our pi. Okay. Now, what we're going to do with our R's here is the same thing we did the R's in the cylindrical shells idea here, is that we're going to say that, well, we've got R1, right, and R2, right? It's R1, R2. We're going to just set R is equal to the average of R1 plus R2, okay? And because I'm going to go ahead and say that that's true, right? I can't just divide by half, right? I'm going to put a 2 in there. So I'm going to say 2 times that, okay? And we're just going to say R is just the average of both of these, because the R's, like, look back at our original picture, right? We have an R1 and an R2. We're going to shrink, right? We're going to shrink this down. R2 minus R1 is going to be a very, very small thing. So we're just going to shrink them down and use the average and call it R. Okay, shrink the distances together here. So we're just going to call this thing, we're just going to say, well, this is 2R. Okay, because R1 plus R2 over 2, right? Let's go ahead and get rid of that. We'll say 2R is equal to R1 plus R2. Okay, average. Times L2. Yes. Okay, and that is equal to my area. Oh, there's a pi. So rearranging a little bit, my area is equal to 2 pi r L2. So that is the surface area of my frustum. This is the surface area of the frustum. So we have, right, this thing. Okay. Here's my radius, average radius. Okay, that's my R. And then here is my L2. Now I'm trying to draw the L2s not like as they're straight lines, because really what we're going to say instead of L2 is we're going to say, well, that's actually the arc length, the one we learned yesterday. That's ds, right, of the side here. So we're just going to be adding up, right? So if you think about this as cutting it like this, we're just going to be adding up all of these R times, right? R times all of these arc lengths. Okay, so we're just going to sum up, right, all these little pieces. So we could think about it as this way, right? We have 2 pi, and we have a bunch of R's. Well, what is R, right? When I draw us our little calculus curve here, this was my R. What is this? This is y, isn't it? This is y equals f of x. So this is the sums of all the f of xi's, right? Because we're going to have a bunch of those. And then we're going to have the surface areas, okay? And let's see, is it time to go through and enter these surface areas? Oh, I believe it is. And then this is the surface area, which is 1 plus f prime of xi's squared. And, oops, not that x yet, that x. All right. So all we're going to do now is we're going to shrink these guys down by tiny amounts. We're just dealing with those little slivers, right? We're going to start adding those up. And now we're going to get integral from a to b 2 pi f of x square root 1 plus f prime of x squared, take the square root, dx. And that is our formula for surface area of revolution. Right? So that's the one we got to memorize. Right? There's a little bit easier of a way to do this. Okay, so if you remember, okay, that the y's are just, the distances. So we could say something like x equals a to x equals b, right? We have 2 pi y square root 1 plus dy by dx squared, and then we have a dx here. Means variables we are integrating with respect to x. Right? We don't have to just revolve around one axis, right? We could revolve around the other axis, or we could change it because surface area was nuts, right? So, or we could do y equals c to y equals d of 2 pi y. This is still revolving around the x-axis. Square root of 1 plus dx by dy squared dy. And integrating with respect to y. All right, so however this is presented to you, you have some options sometimes. Okay, you could either write y is equal to f of x, or you could leave y as y and then do dx by dy, and that's if we're revolving around the x-axis. Okay. We could also revolve around the other axis, but you know what? Since that 1 plus dx over dy squared was equal to 1 plus dy by dx squared was just equal to ds, that's the arc length. We can just replace the formula by arc length and not worry about it so much. Okay. So my surface area is equal to integral 2 pi y times ds. And this is revolved around the x-axis. Or you can have a surface area of 2 pi x ds, and this was revolved about y-axis, right? Because we have that same argument. If we have something here that we're going to rotate around, and that radius, that distance there, that's x. Okay, or f of y. So whatever's going to be easier for us to work on, that's how we're going to do that. Normally, we're not going to do a lot of, well, let's be clever and work it this way. Okay, normally, I'm just going to take the problem as dealt and just work it the way that they kind of expect you to do it, because I know, especially at the beginning, working these things can be a little confusing, a little difficult to picture. So we're just going to work this way, work these as simply as possible, and not try to pull any geometry tricks of trying to make this easier. You can, but I think at the beginning, like, let's keep the training wheels on and learn how to do the problems, just how they're dealt off the top of the deck, and not worry about, well, if we look at it this way, then we can. No, we're just going to go ahead and do that. Just straight up, not pulling any tricks, not doing anything weird. Okay, so that being said, let's look at the function y equals e to the x, and we're going to go from 0 from x to 1. Okay, so let's draw a little picture. Okay. X is 0, e is, right, e to the 0 is 1. And from 1, we're going to be up here at e, right, e to the 1. So we're just going to be looking at this thing. Okay, so from 0 to 1. So the idea here is we're going to take this piece here and we are just going to rotate it about the x-axis. Okay. And I would like to figure out the area, right, of this cup, okay, sort of thing. Okay, so let's go ahead and set that up. So my surface area, right, is equal to integral from 0 to 1. Right, I've got 2 pi. My radius, right, which is y. My radius times the surface area, right? This is times L, right? This is times L for this is surface area. That's the square root of 1 plus. Take that derivative. Dx. Okay, so my x was the radius, right? Y rather is the radius, which is e to the x. And then this bit in here, right, is the surface area for e to the x. Okay, so let's clean that up a little bit. So we have surface area is equal to 0 to 1, 2 pi, e to the x, square root 1 plus e to the 2x dx. Okay, what could be easier? Oh, I wish you wouldn't have asked. So let's go ahead. Let's let u is equal to e to the x. Then du is equal to e to the x. Equal to 2x? You'll see. When x is equal to 0, u is equal to e to the 0, which is 1. When x is equal to 1, u is equal to e to the 1, which is e. Okay. So let's go ahead and do this. So you see that our, what do we have here? We have our e to the x and dx here. That's my du. Okay, so I can just sub that out. Okay, so we have a surface area is equal to 2 pi integral. Oh, we have 1 to e now of 1 plus u squared, right? E to the x dx is du. Okay, so that's why I let just e to the x equal, or u equal e to the x, because I knew that we were going to have this thing going on. Okay, that the du for e to the 2x is going to be 2 e to the 2x. That will help. Okay. If only there was a way to do integrals with square roots. Okay. Like, oh yeah, that's why we learned triangle integration. Because we're going to have theta, we're going to have u. Here's 1. Here's the square root of u squared plus 1. All right. And since tangent of theta is equal to u over 1, u must equal tangent of theta. So du must equal secant squared theta, d theta. Okay. So let's go ahead and do this. We have surface area is equal to 2 pi. Okay, I'm not going to worry about the limits of integration just yet because we're in the middle of triangles, so we're going to hold off on that. But the square root of 1 plus u squared over 1, right? That's the hypotenuse over the adjacent. Is the hypotenuse over the adjacent equal to the secant? And then du was secant squared theta d theta. Not again. I know we just did this one yesterday, so I'm going to cheat. I'm going to say my surface area is equal to the average of, right, the derivative of the secant times the integral of the secant, because that's what it turned out to be last time. So this was secant theta tangent theta plus natural log secant theta plus tangent of theta. And we're going to have our limits here. Okay, oops, we need a 2 pi up here. Okay. Just pointing out that, you know, secant cube might be a thing you want to memorize how to do. Okay, just, you know, giving a fair warning there. Okay. So what are we going to end up with? Okay, we're going to end up with surface area is equal to, what do we have? We have pi, because those canceled. We have pi. And then we have, okay, what's the secant of theta? Secant of theta is hypotenuse over adjacent, so that's square root of squared plus 1 times, what's the tangent? U over 1, so times u, plus natural log of, what's the secant? X squared plus 1, or rather u squared plus 1 square rooted, plus what's the tangent? U. And now we can go back to those limits of 1 to e. Okay, because now we're back in the u world. Okay, so here we have surface area is equal to pi. We have, okay, this is, let's do that. So this is going to be u evaluated at e. So it's going to be e square root of e squared plus 1 plus the natural log of e squared plus 1 plus e. All right. Minus, this is going to be u evaluated at 1. So here we have square root of 1 squared plus 1 times 1 plus the natural log of the square root of 1 squared plus 1 plus 1. All right. So let's just clean that up just a tiny bit here. So we've got surface area is equal to pi. We've got e squared plus 1 plus natural log, e plus the square root of e squared plus 1. I only changed the order because it just felt like it would be easier for somebody to read it. Minus square root of 2, right? Minus natural log of square root of 2 plus 1. Okay. Or 1 plus root 2 would be fine as well. And I'm sure that that is a delightful looking number. There's your answer for the surface area of that shape that we have there, right? That's this thing. All right, and that's my, this side is e to the x here. Okay. So there we go. So that's our example. All right, let's try one that's a little more tame, because that one, that one looked innocent, right? So like, let's just figure out what's going on here with e to the x. So innocent, and then it turned into this mess. Okay, so let's try another one. Let's do y is equal to square root of 6 minus x. I think this one is a homework problem in your book. For x equals 4 to x equals 6, revolved about x-axis. All right. So let's draw it and figure out what we're looking at here first. Okay. So we got 6 minus x. So we've got a horizontal thing going on here. That's going to be 2, 3, 4, 5, 6. Okay, because if x is 6, we have 0. And then we're going to draw our square root. Okay, so we go from 6 to 4. All right, so we're trying to figure out the surface area of this thing revolved around the axis. Okay. So you can think about, it looks like kind of like a cup. I guess you get out of a bathroom or something, like kind of a cone type cup. But yeah, there we go. Okay, like when you're brushing your teeth, kind of a thing, right? Those cups. Okay, those are actually easier because they're just straight. But maybe if somebody sat on them and they turned into a parabola, right, or a square root, that would be those kinds of cups. Okay, we wanted a surface area of that. Why would we want to do that? for the life of me, I don't know why we want to know that for that scenario, but you know, things to think about when you're brushing your teeth, right? All right, so first things first, let's go ahead and write y is equal to 6 minus x raised to the 1/2. Y prime is equal to 1/2 6 minus x to the negative 1/2 times negative 1, negative 1/2, 6 minus x to the negative 1/2. Okay. All right, so let's go ahead and set this thing up. So we've got our surface area is equal to 2 pi integral from 4 to 6. Okay, and now we're going to have our r, which is right, our y. So that's 6 minus x. Okay, and then we're going to have our length, right? And this was ds. So this is 1 plus. And then I've got this whole thing here, negative 1/2, 6 minus x to the negative 1/2 squared. dx, because my limits are in x's, we have a whole bunch of x's, dx. Okay, so I'm just trying to do this to kind of give you an idea of like, okay, it's 2 pi times the radius times the length. That's how we're getting our surface area for these frustums that we went through at the beginning and set all of these things up. Okay, so I'm just trying to keep the pieces to kind of relate to what we were doing at the beginning. Okay, that will help you remember the formula and deal with that. Okay, so surface area 2 pi 4 6. We've got 6 minus x here. All right, let's deal with this mess. All right, so that's going to be, let's just actually, let's not even write this down yet. We're just going to deal with the surface area business and work on that. Okay, so just a little sidebar. Surface area simplification. Okay, so here we have 1 plus squaring this thing, right? That's 1 over 4, and then 1 over 6 minus x square root. All right. Oh, no, not square root. We're squaring it. Okay. You have no idea how nervous I get when I look up at the top and wonder whether or not I'm recording. Okay. So what are we going to do next? We're going to say, well, this is going to be 4 6 minus x over 4 6 minus x. That's a fancy way to write 1, right? And we're going to add 1 over 4 6 minus x. All right, so that is equal to 24 minus 4x plus 1 over 4 6 minus x's. Okay, all I did was combine common denominators here. So 24 plus 1 is 25 minus 4x all over 4 root 6 minus x. Okay, so that's inside of, or no, not root, just 6 minus x. Stop it with the roots. All right, but all of this is inside of a square root. Okay, so that's something to remember. So what I can say is that this is equal to 25 minus 4x times 1 over 4 6 minus x. All right, so back to original. So remember, we had 2 pi, we had 4 to 6, we had a square root, right? We had 6 minus x square root here, times, and then this is the result, right? This is the result of my whole thing here. So we have the square root of 25 minus 4x times 1 over the square root of 4, 6 minus x down there. And I can even say that the square root of 4 is 2. Right? So that's where this went. Right? This 4 turned into that 2. Right. integral from 4 to 6. I'm going to write this one first. Then we have the square root of 6 minus x. Then we have 1 over square root of 6 minus x dx. Isn't that nice the way that turned out? See, you guys thought this was going to be a hard one. Okay. So here we have pi. We have integral 4 to 6 of the square root of 25 minus 4x. We don't even have squares in this one. So we're just going to go ahead and say let u is equal to 25 minus 4x. du is equal to negative 4 dx. Okay. So dx is equal to du over negative 4. Okay, so substituting, we're going to have negative. Oh, when x equals 4, u is equal to 25 minus 4 times 4, 16, which should be 9. When x equals 6, u is equal to 25 minus 24, which is equal to 1. All right, so we have 9 to 1. It's because it's negative. Okay, we have u to the 1/2 power, and then dx. Dx was what? Dx was u over negative 4. So what I'm going to do is I'm going to pull this 4 out in front. And then to the negative sign, okay, what happened here was we changed limits because negative sign. Okay, u to the 1/2 du. It's Calc 1 problem now, isn't it? And this is going to be u to the 3/2. We have a 2/3 from 1 to 9. Okay. So we have 2/3 times all of this, right? So that's going to be pi over 6, right? Because that 2/3 is that. This is a times, by the way. There's not a sign. So that's going to be a 2 here. 2 times 3 is 6. We have pi. And then we have u to the 3/2. So that's going to be 9 root 9 minus 1 root 1. That's what 3/2 mean is, right? Something to the 3/2 is u times u to the 1/2 is equal to u to the 3/2. All right, so this is pi over 6. We have 9 times 3 minus 1. So it looks like we have pi over 6 times 27 minus 1, which is 26, which is 2 times 13. So we could say it's 3 times 2. We have 2 times 13. Those cancel. So we have 13 pi over 3. And I think we're okay there. All right. I think that's probably enough. That derivation was a little long, and I apologize for that. I think this is a good problem to work on. The E one is too, but maybe setting up that one instead of carrying it out would be a better question to ask. Because I really don't want to make you do secant cubed like more than a couple of times on an exam, because it's long. Okay, so I'm going to stop us here. And I will see you guys tomorrow, and good luck and study hard, and let me know.